Alright, welcome to the next video for Algebra 1 at the Gower School. This one is going to be about translating points. So we're not going to be talking about the entire graph itself, just individual coordinate points. So it's actually quite simple, and it's, I think, exactly what your intuition would tell you. To move a point, all you do is change its xy coordinates. So if you have, an xy axis, and here's your point, say it's at 2, 1 or something. If you want to move it, say left 1 and up 2, you're going to subtract 1 from the x-coordinate. So say you want to go left 1, then you subtract 1 minus 1 from the x value. So the new one, if you went left 1 and up 2, say you want to go up, you're going to add plus 2 to the y-coordinate. So it matches your intuition, I think. And your new coordinate point over here, after going left 1, you'd be at 1, 3. So I'm not going to spend a lot of time belaboring this point, but the change in x value is side to side. So if you want to go left or right, this is going to be affecting the x value, left or right. And the change in the y value is obviously going to be up and down, because the y-axis is up and down and the x-axis is side to side. So take any individual coordinate point. If you want to move left, subtract a certain amount. If you want to go left 5, subtract 5 from the x value. If you want to go right, add some number to the x value. If you want to go up, you're going to add to the y value. If you want to go down, you're going to subtract from the y value. So this really should just match your intuition, and there's nothing really too complex about it. Okay, I don't need to do examples. Okay, translating graphs. So translating individual points matches your intuition. You can slide them around. You can even, if you're not sure, you can graph them and then move them and see where they end up. And that will always give you the right answer, and it's very intuitive. Translating an entire function, though, actually ends up leading to kind of results that you might not expect. And so it's a little bit more tricky, because instead of changing numerical values of the x and y coordinates of a point, you're moving an entire function that has variables in it. And so I'm going to show you here in this video how to do it, and then in class we're going to go into why this works, because it's a little bit counterintuitive. Okay, so if you have a function of the form y equals f of x, so that could just be, let's use as our basic example, straight line, y equals mx plus b. If you want to move up, okay, it's intuitive that you're on up and down is going to be the y variable, so that's good. So you're going to replace the y variable with y minus k in order to move up k units. So your new equation would then be y minus k equals mx plus b. Okay, and so what that's going to do, by replacing y with y minus k, if you have this new equation here, if you graph it, it'll be the same graph but shifted up however much k is. So k is going to be some number. So I didn't say it on the slide, but let me write here. K or h are numbers. So it's the amount of distance that you want to move it up. So maybe you want to go up 3 units, then k is going to be 3. You'll put in y minus 3, or something like that. This one is okay to see, because if you were to solve for y, you'd have to add k to both sides. So you can go plus k, and you can see that what you ended up doing was you kept adding the k value to the y-intercept. So whatever your y-intercept was, you added k to both sides, which moved it up. So that should match up with your intuition. To move down, you're going to replace the y value with y plus k. So you'll have y plus k equals mx plus b. And again, you can see that if you were to solve for the y variable, you would subtract k from both sides, minus k. Then you'd have the original y-intercept, you'd be subtracting a certain amount from it, which would move the y-intercept down, which would take the entire graph and move it down. So all the plotted points will get shifted down together, so that they have the same overall shape, just slid down a certain amount. To go left and right, you're going to replace the x variable. And we use the letter k to represent up and down distances, and we use the letter h to represent left and right distances. That's just a convention. I know it's maybe a little annoying right now, but I promise that it's really useful, because when we get onto more complicated graphs later on, h and k are used commonly to represent horizontal and vertical shifts. So starting to think about them that way now will make a big difference in understanding things better later on. So to move right, you're going to replace the x variable with x minus h. So here you would have y equals m, Now this is important that you put it in parentheses, x minus h plus b. Okay, so the m value is going to get distributed in. That's really important. So the substitution from an x to an x minus h is what causes the shift left or right, well in this case to the right. But then if you're actually solving the equation so that you can simplify it and then graph it, you're definitely going to need to distribute the m and then combine like terms to get your new intercept and see where the graph goes, or a new slope, or whatever it looks like. And then to move left a distance h, you're going to replace again x because it's left and right. But to go left, you replace with x plus h. So what to do is not actually that complicated. You're just swapping out a certain variable for something else, y plus or minus k, or x plus or minus h. But it's sometimes hard to remember because when you're going up or to the right, you would naturally think that it would be positive because up and to the right are normally positive. But in this case, for up and to the right, you're going to be subtracting, whereas for down and to the left, you're going to be adding. So it's kind of the opposite of what your intuition was. So it's really important to keep separate in your mind translating points, individual points, which you do whatever your intuition tells you. Up is positive, down is negative. If you're translating an entire graph or function, though, you do the opposite of what your intuition would tell you. To move a graph up, you actually use y minus k, and to move a graph down, you use y plus k. So again, I know at first you might be thinking, what the heck, like why do we do it this way? And I promise I'll explain it in class and it will make sense. But for the sake of this video, just as an introduction and then as a review later on, I'm just going to go straight into the examples so as to not waste your time. Okay, so let's start with a graph y equals 2x plus 3, and say we want to go left 2. So to go left 2 units, we're going to replace x, because it's left and right, with x plus 2, because if we're going to the left, we do the opposite, which is plus 2. So I really want you to show this kind of work when you're doing your problems. Write down your original equation, maybe label that the old equation. Write down what you want to do, how you're going to do it, and then write down your new equation. So our new equation is y equals 2. I'm going to put an x plus 2 in place of my x, and then plus 3. Okay, so here's my new equation. Now I want to simplify it. I'm going to distribute this in here. So 2x is 2x. 2 times 2 is 4, plus 3 is 7. So my new equation is y equals 2x plus 7. My old equation was y equals 2x plus 3. Now if I'm going to graph these, I'm going to go up 3 for the old equation, and my slope is 2. So I'll go up 2 over 1, up 2 over 1, put my dot, down 2, backwards 1, down 2, backwards 1, down 2, backwards 1. That's probably enough, so I can draw. I apologize. Wow, that's that's a bad line. I don't have the ability to erase, unfortunately, right now, but my first line was really terrible, and I apologize. I'm trying to draw it through all the dots that I made. That's why I make so many dots when I'm doing my graphs, because it helps guarantee my line will be accurate. So I'm going through this point right here, 3. Now if I move this line left 2, every single dot is going to get moved left 2, and you'll see that when we graph the new one. So y equals 2x plus 7, my intercept, instead of being at 3, 4, 5, 6, 7. So here's my new intercept. If I go down 2, backwards 1, down 2, backwards 1, down 2, backwards 1, down 2, backwards 1, down 2, back 1, you can see that every single point got moved left 2, left 2, left 2, left 2, left 2. So even if it doesn't make sense yet why it works, you can certainly see that it does work. And so if I draw this line through here, we should put arrows on the end of our lines to show that they go on forever, and we should label this one new, and we should label this one old. So you should always have an old equation, a new equation, what you did, an old line, and a new line. Those are the 5 kind of key aspects to any of these kind of graphs. Okay, let me do one more example. Let's do y equals x squared, and let's move this guy up 2. Let's just move him up 3, so it'll fit a little better. So the old graph, y equals x squared. To move up 3, we're going to replace y, because it's up and down, with y minus 3. Okay, because you do the opposite of whatever you would have normally thought. So this is our old graph, our old equation. To get our new equation, we'll put y minus 3 in place of y. So this y right here is getting replaced with y minus 3 x squared. So all we're doing is we're swapping out in place of y a y minus 3. Now we can add 3 to both sides, and we can get our new equation, y equals x squared plus 3. So it's not too bad. To graph the old one, remember that for a regular parabola, the vertex or starting point is 0, 0, because 0 squared is 0. You go over 1, up 1, over 2, up 4. So let's label that as a 4. Let's label that as a 2. It's always important to label your axes if they're not already labeled. And we go back 1, up 1, and we go back 2, up 4. Okay, so that's enough. Hopefully I can draw this in pretty well. There's that side, and there's that side. Okay, so now to draw the new parabola, all I have to do is look at what I did. So I don't have to really worry about how complicated my equation might look, although in this case it's pretty simple, but it could look really complicated depending on what you've done. But the way to graph it is to just look at the transformation you made. We moved up 3. So instead of starting at the 0, 0, I'm going to move up 3, and I'm going to start right here at 3. But once I know my new starting point, the way that I get to all the other points is the same. So from the vertex, I go over 1, up 1, or I go over 2, up 4, or I go back 1, up 1, or I go back 2, up 4. And then I can draw all of these lines in as well. And so this parabola here, I mean my picture is not perfect because I'm on a computer, but this parabola here, if you take that whole thing and you shift it up 3, it will then take this place of this parabola here. And you can see that point by point. This point moved up 3, this point moved up 3, this point moved up 3, this point was also up 3, and this point was up 3. So every single individual point translates or moves up or down or left or right the required amount, and then in effect the whole graph moves that much. Okay, so you're going to be doing lots of transformations for parabolas and linear equations, both left and right and up and down. And the key is just to remember that if you're going left and right, you use the x variable. If you go up and down, you use the y variable, and you do the opposite of what you think. So if you normally think up is positive, in this case you're going to replace y with y minus a certain amount. Okay, so good luck, and ask questions in class if you have any.